myself. Name's Josh Riniger. I've been with EBTRON for almost 10 years, background mechanical engineer, and I currently am the West Coast manager for EBTRON sales. And during this presentation, like Sean said, if you have any questions, feel free to type it in, and we would be happy to answer your question at the end of the presentation. I'm going to turn off my camera during the presentation just to ensure, that we don't have any connection problems with the internet. So let's get started. So we're EBTRON, again, like Sean said, we are a thermal airflow measuring station. And today we're really going to try to hit on the importance of airflow measurement for IAQ. So why measure, and then what are some of the EBTRON solutions that we have for you as a design engineer, as a ATC contractor, or why is this important if you're an owner? So these are the learning objectives. We're going to go over some industry updates with regard to COVID-19. What are certain engineers doing with their designs? We are going to look at some benefits for certain contractors by utilizing the EBTRON product line. We're going to go over demand control ventilation and how to improve your DCV strategy if that's something that you're using. And then again, the EBTRON solutions. We have a solution for every application at all different price points. So we'll go over some of those solutions in terms of what we're talking about today and how we can help you. All right, so why measure airflow rates? And I've broken this down into 4 separate categories. And, like I said, I have mechanical engineering background. And when I was in my mechanical engineering classes and labs, I remember, using airflow measurement. It was a differential pressure device, and actually it was for fluid dynamics lab in terms of measuring lift and drag over an airfoil wing. But when I started with EBTRON, I was wondering, why is this such an important thing? And it had been about a month working with EBTRON, and we have customer events where customers like yourselves come down to our factory and we do a product showcase. And I was talking to this engineer, and I was saying, we make a really good product. I'm happy to be here working with EBTRON, and he goes, yeah, what you do is really cool. And what you do is also really important in the industry and in the world. And again, I'd only been working for about a month, so I said, oh my God, tell me more. That's not something that I've heard. And he said, proper airflow measurement and proper pressurization control is the difference between an infectious disease spreading out of an isolation room to other parts of the hospital or being contained. So for me, that's kind of when a light bulb went off in my head, and I started to really understand the importance of airflow measurement. But it differs depending on who you are. If you're an ATC contractor, if you're an engineer, or if you're an owner. So this is kind of all encompassing, and I've broken this down into 4 separate categories. Reduce liability, saving energy, how can an EBTRON maximize facility performance and diagnose certain issues that you might have, and improve occupant well-being. And I think that improving occupant well-being is probably the most important one. And that kind of goes hand in hand with reducing liability. And let's go ahead and take a look at this and get started. So let's jump into benefit 1, reducing liability. So all of these building codes, and I have them shown on the screen here. We have the UMC, the IMC, the ASHRAE 62.1. They're all built on the International Mechanical Code, or that specify minimum ventilation rates for compliance. So actually, ASHRAE 62.1 is the point of ASHRAE 62.1 is to specify the minimum ventilation rates for acceptable indoor air quality. And what do these codes do? They tell you what type of ventilation rates you need in certain spaces, depending on your space type, depending on your occupancy, right? So how can you comply with these codes? Well, measuring airflow, you can demonstrate that the system design provides the code required outdoor air ventilation provided to the space. And all of these are rate-based standards. So what does that mean? You're having to design to a certain rate. So how do you demonstrate you're achieving that standard? You have to measure. And let's take a look at this. So again, I talked about ASHRAE 62.1 a little bit. The IMC and the UMC are really strict interpretations of ASHRAE 62.1. You'll see for Massachusetts, the current design is to IMC 2015, ASHRAE standard 62.1, 2013, but these standards get updated every few years. And it's always really best practice to be designing to the latest standard, because eventually that's going to be updated and accepted in your local building code. Now again, what do these codes and standards say? All require that outdoor airflow rates are provided under dynamic load or dynamic reset conditions. So what is dynamic load or reset conditions? That means as the loads in the space is changing, you need to be able to provide the correct amount of outside air. So as more people are coming into the space, you have to be able to provide the correct amount of ventilation air based on that population in the space. And let's take a closer look in ASHRAE 62.1, because basically there's two separate procedures that you can design to as a consultant engineer. You have the VRP, which is a ventilate procedure. This is a prescriptive design procedure where the outside airflow rates are determined based on space type, occupancy level, and floor area. And this is what you typically see a lot of engineers designing to. You also have the IAQ procedure, and it's an alternate ventilation procedure that basically determines necessary outdoor air to maintain certain concentrations of contaminants under a certain level. Right, so you have to do the math and figure out what the airflow rates are depending on the contaminants in the space. Doesn't matter what you design to, both of these are rate-based standards. And what does that mean? Again, if they're rate-based standards, you have to be measuring and controlling to comply with the standard. For the IAQ procedure, we typically see this in lab type of applications, but if you are designing to the IAQ procedure, it's even more critical to measure airflow, because again, a lot of times you're decreasing your airflow rates in the space because you have some other type of filtration, whether albeit specialized filtration, that are removing some of those contaminants as well. Also, your design for the IQ procedure might be trying to downsize your equipment, since there's less load and you have to bring in less amount of outside air. A thing to note about this though, since you are downsizing your air handling units, you have to verify and you have to basically have a report that shows, hey, this is a report that shows these contaminants have been removed before the building is occupied. So that's something to note if you ever need to bring in more outside air and you don't design your system to accommodate for that, right? Those are the two procedures that are really the driving forces in the industry. Again, we want to document that the system provides adequate ventilation during operation. Now you might say, okay, well I could do, maybe I have a two-position setup where I'm looking at actuator feedback, and that's how I'm determining how much outside air I'm bringing in. The issue with this though is fan speed, wind pressure, and stack pressure variations. You also have damper issues. It makes it impossible for really a one-time setup by a tested balancer to satisfy these ventilation requirements. So putting an airflow station in is really like an insurance policy for an engineer to validate your design in the event of IAQ litigation. So let's look at some of these outside factors and show why you really need to measure. So let's look at a fixed minimum position intake damper. And damper, this is just a recirculating air handling system right here. And dampers have issues with them, just like other equipment have issues with them. It's always good to use a high quality damper. But for the issues that dampers see, you have hysteresis, you have binding over time, or you may have deterioration in the seals. So we did a simulation at our factory, and this is looking at going from 0% to fully open back to 15%. And what we're trying to see here is how is the damper interacting with this? So let's take this example a step further. Let's say, hey, you have a test and balancer. He's going out to set up this unit on a Friday. The winds are light and variable. He's setting up his rooftop unit, and he sets it up this way, from 15% to fully occupied during max occupation, then back to 15%. Well, what you'll see here is, yeah, there's a little issues with damper hysteresis. We're trying to maintain this V naught T as set point. This is the ventilation requirement. And you'll say, hey, when you go from open to close, you're right around 100%. Now you're under ventilating a little bit going from open to 15%. But you might say to me, hey, Josh, that's not that bad. I'm right around the ventilation required set point. Well, let's take this a little step further, right? It's Monday morning. Again, the balancer set this up on a Friday. Now it's Monday morning. Your system goes into morning warm-up. Well, now you have a 15-mile-per-hour crosswind going across the intake of this unit right here. Well, what does that do? That creates a negative pressure drop. So when you thought you were bringing in 100% of the set point, now you're underventilating by 20%, and you're not complying with your whatever code or standard you're designing to. This is just another simulation looking at a 15 to 18 mile an hour crosswind. And you can see that if you have a crosswind, you're underventilating when you should be bringing in this amount of outside air to the space. Now, also a direct wind, you're going to be overventilating, and we'll talk about that in a little bit. Other issues that we see is stack effect. Normally, you want to maintain your building to be slightly positively pressurized to eliminate stack effect. Now, in the winter, for buildings greater than 4 stories, you'll have winter stack effect. What happens, you have a dense, colder column of air coming up through the bottom of the building, infiltrating your plenum, putting strain on the outside air being supplied to each space. You also have the same issue in the summer, where we call this reverse stack effect or summer stack effect. A lot of times, this is not as bad because the temperature differentials between the, your bottom floor and the top floors are not as bad. So like for Boston, winter stack effect could be an issue. So this is just looking at a simulation again, 70-foot low rise with 100-degree differential. Again, in the summer, you're overventilating, and in the winter, you're severely underventilating the space if you're not controlling the outside air intake, right? So what do you want to do? You really want to measure and control your flow rates. And what engineers are doing for stack effect is there's never a way to completely eliminate it, but they're doing zone and floor level control. And then they are compartmentalizing with basically a damper flow meter combination, again, on each zone or each floor to help mitigate some of those stack effect issues that you will see. So you really got to measure outdoor airflow rates because you have all of these issues, and you have to control them to make sure you're bringing in the right amount of outside air to the space. Now, this just looks at, the simulation I was talking about earlier. When we measured it with a flow meter and we controlled that damper, we were right at 100% of the desired airflow set point. Now, one of the biggest lawsuit problems in the world is mold growth in buildings. And this is typically created from pressurization problems and outside airflow problems, right? And this can lead to poor occupant health. We're talking about IQ, and again, litigation. I was actually doing a presentation for basically the Virginia Society of Healthcare Engineers this past summer. It was basically the ASHE group of Virginia. And one of the lunch speakers was basically a contracting group, and all they deal with is mold remediation in spaces. And they actually talked about a huge project that they had to work on, and it was a hospital, and obviously they didn't want to disclose this, but it was obviously somewhere in Virginia. And what they did to mitigate the issues with mold, right? And mold had already formed in there. But how can we try to eliminate any type of mold or fungal growth potential in the space with airflow measurement? So ultimately, like I was showing with the stack effect slide, we want to maintain our buildings to be slightly positive, because if they're slightly negative or negative, we are able to bring in unfiltered, untreated air through walls of the space, right? And what does that mean? Well, if it's a hot, humid day, you're bringing all that humidity in the space. You're going to have temperature control problems in your space, humidity control problems in your space. So we want to maintain the building to be slightly positive. And this is just showing an example, like in the summer when you're doing cooling and you have a negative space, you're bringing in this moisture to the space. And normally for mold and fungal growth, favorable conditions are above 65 degrees Fahrenheit for your dew point temperature. And as you'll see, even in the Massachusetts area, that's almost 10 to 20% of the year where you have these conditions favorable for mold and fungal growth. And what does that mean? That means, almost 2 months out of the year, if you're not maintaining proper building pressurization, that could lead to potential mold or fungal growth in your space. And what does ASHRAE say about this? Well, ASHRAE says under Standard 62, under Systems and Equipment, Section 5.10, it says that anytime the outside air dew point temperature is above 60 degrees F, you have to be providing controls to dehumidify the space. And why are they saying this? Because of potential for mold, of potential for fungal growth, if you're having humidity control issues and temperature control issues in your space. So what you want to do in terms of building pressurization is put a flow meter on your supply, return, and outside air and be able to control your flow rates. All right, so we talked about, hey, it's important to bring in the proper amount of outside air, comply with your codes and standards that are built upon providing proper indoor air quality. But we also don't want to bring in too much, right? Because the cost to condition outside air can be expensive. The Department of Energy states it can be anywhere from $2 to $9 per CFM. And what I see, especially moving forward with this whole decarbonization pitch, that more and more owners are going to be concerned with wasted energy in the space. And we're kind of getting through COVID. We're going to talk about that a little bit, but we have been trying to bring in as much outside air as possible to certain systems for dilution ventilation to try to mitigate any issues with COVID. And once the pandemic kind of comes to a close, there's going to be a push more towards energy savings. So how can we help? Again, we want to avoid overventilation of outdoor air without compromising indoor air quality. So let's talk a little bit about DCV. So what is DCV? So the demand control ventilation basically is bringing in the required amount of outside air to the space based on the space type and based on the population, right? So you are staging your system to bring in outside air depending on the population of the space. And traditional methods for this are a CO2-based DCV strategy, where typically you're maintaining around 1,000 or 1,100 parts per million to the space. But let's look at how we can improve that, because there are some issues with that, right? What does ASHRAE say? So ASHRAE says that DCV shall be permitted as an optional means of dynamic reset, and that for DCV zones in the occupied mode, the breathing zone outdoor air, BBZ, shall be reset in response to the current population. So again, as the population is changing, the required amount of outside air is going to change to the space. This is a typical fixed set point CO2 DCV strategy, and we're assuming steady state, we're assuming no lag, we're assuming no air associated with your DCV sensor. We're assuming an outdoor CO2 rate of 400 parts per million. and we're assuming a CO2 production rate based on average males 20 to 60 years old. So again, this is what a lot of designs typically do. Here are some of the issues with this. If you calculate this scenario by using ASHRAE 62.1, the ventilation rate procedure, you should be providing this amount of outside air, the black line, based on the population. Well, using this CO2 DCV strategy, you're under-ventilating at low populations, and you're over-ventilating at high populations, thus wasting energy right here. Now let's take a look at a typical CO2 sensor where you have uncertainty, right? Well, you are significantly over-ventilating at the higher populations right here, and you're still obviously under-ventilating at lower populations based on this CO2 error for the sensor. Again, you're going to have wasted energy, thermal comfort issues going into your space because you're going to have hot, humid air coming into your space, and you're going to have IQ problems. You're not going to be complying with codes and standards here at the bottom on the low end at lower populations, right? So how can we help you with airflow measurement? Well, a couple things. So first thing I always recommend to design engineers is specify a self-recalibrating CO2 sensor, because all CO2 sensors drift. We have one, but a bunch of people make CO2 sensors out there as well. The second thing to do is limit your max and min flow rates based on the space type of application and the max population on the high end and your min population on the low end, right? That way, you are never over-ventilating your space, you're never under-ventilating the space, and everything in between you are controlling with your CO2 sensor. So that is a control strategy that certain engineers are implementing, again, to save energy and not under-ventilate the space on lower populations. This is just the control logic for this. We have this if you need it. It's going to skip through this pretty quick. And another area where you can even take this a step further is to directly count the people coming into the space. Now, sometimes this is known depending on building types. Sometimes you have a point of sale, you have turnstiles in arenas, you know the number of people coming into movie theaters. So you can stage your air handling unit to bring in required amount of ventilation based on the population in the space. Now, what we make at EBTRON is we make a population counter. It's called the census counter, and that has an uncertainty of plus or minus 3%. But if you look at it here in this simulation, it's way better than the CO2. The CO2 readings right here, we have more uncertainty. So think about doing population. The other thing that I didn't even hit on yet is lag error associated with CO2 sensors. All CO2 sensors really have an inherent lag. It's about 20 minutes. So, if you have a big gymnasium and you have a CO2 sensor on the wall, first off, it's dependent on where it's placed. Secondly, it's dependent on where the people are. If you have a huge gymnasium, well, it might take a long time for that CO2 sensor to reach the production rate of 1,000 parts per million to actually start ventilating the space. And again, you have a 20-minute lag on top of that. On the back end, when people leave the space, there's still that 20-minute lag. So a lot of times you will be ventilating the space based on 1,000 parts per million where you have no occupants in the space. So that's also another issue with the CO2 sensor. This is, again, the control logic if you are using, for example, the EBTRON product, the census, and measuring the population. Another benefit is saving energy. We make a product that also has a humidity sensor in it for your economizer control strategy, be it enthalpy, be it if you're using fixed tribal economizer control strategy. And we're going to talk about that in a little bit, how that's a benefit to engineers and contractors alike. One thing that I think is really important, and we're seeing a lot more nowadays, especially with big facilities, be it campus universities, is how to improve the facility performance and the facility efficiency. And again, I said you can't control what you can't measure, what you don't measure, but you can't manage what you don't measure. I talked about the issues with dampers, right? You have hysteresis, but you also have dampers that bind over time. You have economizers that don't always work. You have fans, you might have a fan array, and you have fans that might fail within that array, right? So airflow is a really important indicator for facilities managers. And what you really want to do is use an airflow station on your supply, on your return, on your outside air to diagnose any problems. And obviously, again, demonstrate you're providing the right amount of outside air to the space. We also have an EBLink tool, which facilities managers love, which controls contractors love, and also engineers really like as well. Because you can see everything in live time of what's going on at the EBTRON unit. Has about a 20-foot radius. Basically what you do is you download a Bluetooth app from your Apple or your Google Play Store. It's called the EBTRON EBLink. It's a free app. And for all of our Gold Series products, you can see what's going on at that transmitter. You can do a traverse, because what we do at EBTRON is we measure at each individual sensor node airflow. We're going to get into that in a little bit. You can do a traverse, and you can also do a diagnostic screen if you ever have any issues with, the flow meter. You think it's the flow meter that's having an issue. Before getting on a ladder, you can connect to this with Bluetooth, download the diagnostics data, and shoot this over to our service department who can help you out. Engineers, what I'm seeing some of them do with this device is they're asking the commissioning agent to send them a report once the building's commissioned. And why is that? They want to verify that their system is meeting the design flow requirements on day one. And once you have all this data, again, you can save it directly to your phone. So engineers love that, because if anything ever goes wrong with their system, they can say, hey, day one, this is how it was commissioned. This is what the flow meters were reading on day one when this was commissioned. Contractors really like this because they don't have to get up on a ladder anymore to actually go through the menus of our transmitters. They can connect to this again on their phone, do diagnostics on their phone first. Another feature that we have on this is, if you do a field adjustment with our products, we don't recommend doing it unless it's greater than a 10% error based on the tested balancer. But if there is any type of offset or gain put into our products, you can see what are the factory calibrated settings by disabling a flow adjustment right here on this button right here at the bottom. All right, so, and we'll talk about this here in a little bit as well. But now let's move to the last benefit, improving occupant health and well-being. And again, I think this is one of the biggest benefits for indoor air quality, for airflow measurement in spaces. And ultimately, we want to make the buildings healthier and safer for occupants. So here are the steps to acceptable indoor air quality. The first thing you got to do is you got to know what are the contaminants of concern in the space. So you have building generated, you might have VOCs based on the building materials in the space. You have outdoor generated, and you have occupant generated, right? Well, you want to maintain those contaminants below threshold levels. So I have this as the 3 R's: reduce, remove, replace, but really it's dilute. And that's where EBTRON comes into play with dilution ventilation. And then what you want to do is follow these applicable industry standards, codes, and rating systems. And these are put in place, again, to help provide acceptable indoor air quality. So these standards are set forth as design standards if you're an engineer. Now, we all, like I talked about, we've been in this COVID pandemic for almost 3 years now, and a lot more people understand that ventilation is important. I just saw an article a couple weeks ago on CNN, and it said the invisible COVID-19 mitigation measure is finally getting the attention it deserves. It said a powerful mitigation method for COVID is ventilation, basically. So, the public is becoming more and more educated in understanding that ventilation is important. That's why, during the pandemic, people felt more comfortable sitting outside when they went to a restaurant. That's why there was really no mass super spreader events when people were outside. It's because basically there's unlimited dilution ventilation. So how can EBTRON play in this? Well, what does ASHRAE say? So ASHRAE came out with a position document back in 2020. They were really quick to come out with this and address the issue. It was April 2020, and there's been a couple revisions, I believe, to it. But what did they say? They said under section 1, what's the issue? Well, dilution, extraction, ventilation, pressurization, airflow distribution and optimization, mechanical filtration, UVGI, and humidity control are all effective strategies for reducing the risk of dissemination of infectious aerosols in buildings and transportation environments. What does that mean? That means we can help by providing dilution ventilation for reducing the risk of infectious aerosols such as COVID-19. They go further into talking about it, and they talk about that, pathogen dissemination does occur through the air. And they say, while ventilation systems cannot interrupt the rapid settling of large droplets, they really can influence the transmission of droplet nuclei. So what does this mean for us? Well, typically, when we breathe out, larger particles normally fall to the floor within a few minutes. And if you'll notice here, ASHRAE recommended, or they said, droplets travel about 3 to 7 feet from the source. And that's why during COVID, there was that maintained 6-foot distance, right? But also you have desiccation occurring, and smaller particles can suspend in the air for hours or even days. So that's where dilution ventilation really comes into play. And this is ASHRAE's position, and this is the position for non-healthcare buildings. We're just going to hit on non-healthcare. For healthcare buildings, they want you to increase the air change rates, and we can talk about that if we have any questions afterwards. But let's just look at non-healthcare buildings. So basically, non-healthcare buildings should have an emergency response. And what do they want you to do? They want you to try to increase your outdoor air ventilation to 100% as indoor and outdoor conditions permit, and disable any type of DCV, right? And as a design engineer, this is difficult to do, especially with existing systems, because a lot of times your systems were not designed to be able to carry this type of load. And that's why ASHRAE says, as conditions permit. They want you to try to do the best that you can. But they also say they want you to maintain temperature and humidity as applicable to the infectious aerosol of concern. That's where also EBTRON can help you out. There's been studies that have shown that maintaining a humidity at 40 to 60% is optimal for infectious aerosols, and that kind of goes back to this, right? If you have dry air, those particles can be suspended in the air for longer. So, what are certain design engineers doing to try to provide a solution to this? Well, for one thing, a potential solution is designing to a normal and pandemic mode. So a normal operation mode is basically maintain the required amount of ventilation per whatever code or standard. Let's say, for example, ASHRAE standard 62.1 based on the expected population. And then for high occupancy spaces, kind of like I said previously and showed that graph, improve your DCV performance by maintaining an upper and lower airflow limit with an outdoor airflow measurement device. So that's normal operation. But pandemic mode of operation is control outdoor airflow rates to the system's capacity based on load conditions. Again, disable the main control ventilation. The likelihood that there's going to be another pandemic is probably pretty likely in our lifetime. And again, we keep seeing these spikes with COVID, and hopefully this year, it's not as bad this winter, but last winter it was really bad. So something to think about in your future designs is to design for 2 operating modes. where if there's another pandemic, you can quickly toggle between normal and operating mode, right? So you're providing more outside air to the space, more dilution ventilation to the space. Occupants are going to feel more comfortable in the space as well. All right, so let's get into some of the EBTRON stuff, some of the EBTRON products, and what we do and what are our solutions for the issues that I outlined. So we've been around for over about 40 years now. We pioneered outdoor airflow measurement in the late 80s. And what we do is we do a thermal dispersion airflow measurement. So let's look at thermal, because I think this is really important. And this is really what sets EBTRON apart from other airflow manufacturers. Basically what we have here is we have our sensor node, and we have two thermistors. These are medical grade thermistors. They were actually designed for NASA during the 1960s, the Apollo space program, because they can survive extreme differentials in temperature. We have one thermistor that's self-heated, and we have one that's zero powered, right? And we have multiple of these in our probe, right? So we call this complete package a sensor node. So how do we calculate airflow? Well, we know the power dissipated to the airstream from a self-heated element, and we know the temperature differential from the heated element, and we'll call this the ambient element, right? Well, that forms a proportional relationship to velocity, or really mass velocity. And these are extremely stable parts. Again, they're older parts, but they're extremely stable. We oven age these for 4 weeks for stability. We hermetically seal these inside here for long life. Again, I talked about the Apollo space program. And what do? We submerge these sensors in controlled temperature baths. That way we can determine the precise resistance characteristics of each of these thermistors right here. And then we pot these with a marine grade epoxy, because these are, we know these are going to be in a lot of different applications. There's going to be salt water on coastal environments. There might be some type of atmospheric acids if you're near a plant. So we really go the extra mile to try to make sure these survive when they're installed in the field. One thing again to remember is we use bead and glass thermistors. We're the only manufacturer that does bead and glass. And what do? We calibrate these at multiple flow rates. So for our duct mounted, it's 0 to 16 points from 0 to 5,000 feet per minute. And what you'll see is that even at low flows, we still have a high signal resolution. So that makes thermal really good at reading in outside air intakes because of the sensor signal resolution right here. Now we also calibrate these units to NIST traceable standards. NIST stands for the National Institute of Standards and Testing. And basically we send our unit off to NIST. We get a reported calibration based on their laser Doppler anemometer. We take that reported calibration and we transfer it to our production wind tunnels at the factory. So each one of these sensor nodes are calibrated to 16-point NIST traceable standards. This is just an example of a reported calibration from our production line. And as you see, there's a 0.2% error for this sensor node right here. Now we are very conservative in what we say, and we say plus or minus 2% of reading for each sensor node. But a lot of times they're under 1%. And this is just a specification item that if engineers do like the EBTRON product line, they can put in their specification. Again, we're also a percent reading device. So over this entire operating range, we're going to be able to read accurately. Once it's installed in ducts, we say plus or minus 3% of reading. Doesn't matter if you're at 50 feet per minute or 5,000 feet per minute, we're plus or minus 3%. Now, something that we've come out with, and it's really revolutionary, and I'm going to talk about that because of how we're calculating it, but with our Gold Series units, for duct or for your outside air intakes, we now have the option for relative humidity measurement. And this can read relative humidity, dew point, or enthalpy, right? So this is the ruggedized integral capacitive relative humidity sensor we use. We put this on the discharge side of the probe to make sure it doesn't build up with anything that's coming in from your outside air intake. And it's a plus or minus 2% relative humidity reading over the normal operating ranges, right? Now, all relative humidity sensors drift. So what we've done is, in our menu structure here, if you ever want to recalibrate the humidity sensor, you don't have to pull this out. You can simply calibrate it to a reference device of plus or minus 10% RH right here in our transmitter menu structure. Now, again, I mentioned all relative humidity sensors drift. Well, with the thermal devices though, airflow measurement or temperature measurement, that does not drift over time. So once you install this in our reading airflow, basically set it and forget it, no drift. And this is just, typical system accuracy of sensors that you might be buying in the field versus the EBTRON unit. And again, I said EBTRON measures temperature to calculate flow. So we have to have a really accurate temperature sensor. So our first output is always flow. Our second output is temperature, which is a 0.1 degree F temperature sensor. And then our third output, we have the option for relative humidity, dew point, or enthalpy. So it's an extremely accurate device. And again, now you have 3 points going back to one transmitter. So as an ATC contractor, this is a way to help save money. Instead of buying a separate outside air sensor to put in your outside air intake, utilize the 0.1 degree F sensor of the EBTRON unit, or utilize the relative humidity sensor of the EBTRON unit. Now, if you're doing any type of economizer control strategy, we can help you out with that. And we can help you out with pressurization control as well. So this is just maintaining active relief. This is for a DOAS or energy recovery setup. And you're maintaining the pressurization between the supply and return, right? Because we don't want to have pressurization control option issues. And again, we can also read your temperature, flow, and humidity or enthalpy. Now, let me just go to this. We also have more application-specific products. So for DOAS systems, we have a smaller unit, which is called the EBFlow unit. And why do engineers like to use this? Well, if you have a DOAS system going to single zone, say it's a classroom, you can measure at the terminal unit with the EBTRON units, and you can control the air going to that space. This helps you meet, 90.1, which is the energy standard if you're having turn down requirements in your system, because the EBTRON units, again, can read at really, really low flows and can read accurately. So now you have an extremely high performance, basically VAV control box with the EBTRON units. These are just some type of applications to think about, high-rise commercial offices, hotels, and any type of decoupled system, you can use the EBTRON product. Let's look at some economizer strategies. Now, it doesn't matter what type of economizer strategy you're using. If you're installing the EBTRON product, again, you can use the temperature sensor as an output, and you can also use the humidity sensor if you need that. So this is a fixed dry bulb temperature economizer control strategy. And let's look at this, and let's look at how EBTRON actually calibrates, or not calibrates, but calculates their velocity weighted temperature, and show you how it gives you a really accurate representation of the duct. So we have the sun hitting down on this dual ducted outside air intake, flow coming in. Let's say we're doing a dry bulb economizer strategy, and let's say, your contractor, the sensor that you buy, you're going to install it at the bottom of the duct. It doesn't matter, but for this example, let's say the bottom of the duct. And we have 5,000 CFM on the top of the duct. We have some stratification, and we have 3,000 CFM on the bottom of the duct. And you'll notice 80 degrees on the top of the duct and 70 on the bottom. So if you're doing a fixed dry bulb strategy, anything under 75 degrees, you'd be economizing. So if you're using this sensor, it's separate from the EBTRON, just one that you're normally supplying, you'd be economizing. Well, even if you took 80 and 70 and divided it by 2 and used the temperatures from the EBTRON, you would still be economizing, because 75 or less, right? But if you use our velocity weighted calculation, which is inherent for all of our devices, we're saying there's almost twice as much airflow at the top of the duct based on the bottom of the duct. So we're weighting more value to the top of the duct, right? So using the velocity weighted calculation, you would actually be at 76.3, and you should not be economizing. So when you were economizing, you were actually rejecting air that cost less to condition, right? Let's look at this, right? So again, this is another example of differential dry bulb temperature. It doesn't matter what type of economizer control strategy you're using, we can help you out with that. And again, I talked about ASHRAE standard 62.1, section 5.10, that on your systems, you have to be dehumidifying when the outdoor air dew point is above 60 degrees. We can do that just with your outside airflow meter and using our dew point reading, right? Now, this is fixed enthalpy dry bulb temperature economizer strategy. Again, we can do whatever economizer strategy you need. Let's take a look at this. Again, it's kind of the same as the last strategy where we were doing fixed dry bulb. But if you look at the situation, if you were using an enthalpy sensor by others, it would be reading 26.6 BTUs per pound. And when you economize, you really want to be under 28 BTUs per pound. And even using the average temperature values with the EBTRON units, if you do the calculations, you're still under 28 BTUs per pound. But again, if you use our velocity weighted enthalpy calculation, which is basically taking into account the entire duct profile, then you should not be economizing in this situation. And I can move the numbers around to show, hey, with the EBTRON, you should be economizing. With a traditional economizer sensor, it would show you that you shouldn't be economizing. The bottom line is using the velocity weighted measurements with the EBTRON gives you extremely tight control over your system and can give you energy savings, typically not seen with a traditional sensor. All right, let's go into some of the products and we'll open this up to questions. So I was talking about terminal measurement, for DOAS units coming into, for terminal measurement going into individual spaces and zones. Well, this product is something that you would use there, right? So we have the EF2000T, which is designed really for round ducts, 4 to 16-inch round ducts, plus or minus 3% accuracy. And with all of our products, again, you have flow and you have temperature. And with our gold series, you have that humidity or dew point or enthalpy measurement. So you're always getting 2 points of measurement. So these are really designed for VAV box applications. See these in a lot of retrofit applications where, they're pulling the crossflow rings out and they're installing these. It makes it really a high performance VAV box, again, because these can match your turn down requirements. We have the 2000T just has a display, and the 1000T is just stripped down, no display, but again, plus or minus 3% accuracy. For small rooftop package units, we have the U series right here, and we can also do smaller ERV measurement as well, where we are trying to maintain a pressurization differential between the intake and the exhaust side, right? So both of these probes are going back to this transmitter. Why do engineers use the EBTRON Airflow? Again, so this is what I was showing on the previous slide right here in the center. Well, turn down requirements can meet that. If you're trying to save energy based on 90.1, any type of critical zone VAV systems, this is a really high performance VAV box, and it's going to help with potential energy savings, right? Also, this is a lower first cost for lab type of applications. Basically, we are the VE for labs because this is such a high performance flow meter right here. And with all of our EBTRON units, again, there's no recalibration. So lower maintenance versus cross flow run. You're never going to have to get in there and recalibrate these units. Once you install them, it's set and forget it. Something else to think about, if you're doing VAVs with a hot water reheat coil, normally you want these installed upstream of your VAV box. But if you have a hot water reheat coil, install this downstream of the coil. The coil acts as a flow straightener. Install it 1 duct diameter downstream. Now you're getting your flow, you're getting your leaving air discharge temperature all back to 1 unit. So as an ATC contractor, this is cost savings instead of installing a separate temperature sensor. Again, I talked about labs, lower first cost versus Venturi valve. Again, we are kind of the VE situation for lab type applications. And both for labs and both for hospitals, you know, it's room pressurization control. It's installing these units on the supply and any return, and if there is exhaust, right, to maintain that pressurization if it's an isolation room, if it's an OR room, depending on whatever type of application you were designing. And I did talk about a little bit about decoupled systems previously, and this is basically kind of the same graph, but where this takes it a step further is, you know, you could have a CO2 sensor going back to a controller and modulating the airflow rate at the terminal level based on our unit, and based on the controller, and based on the CO2 reading to the space, if you're using a decoupled system. And you could also do this the same way with our population counting over the door. So think about, you know, like classrooms or schoolrooms. Extremely tight control with using the EBFlow products. And we also have duct mounted products, and you know, this is kind of the EBTRON bread and butter. I talked about the Gold series with the humidity. That's going to give you the most accurate device because we have up to 16 sensor nodes, so we can read an accuracy of plus or minus 3% for ducted applications up to 120 inches by 120 inches. Have the Hybrid series. You know, this I see is more for monitoring. If you're trying to achieve a lead point and you're not controlling, this is a little bit more cost effective than this. And again, this is our more application specific products. We also measure in the fans, and we can do individual fan airflow measurement. And the great thing about this is these never need to be recalibrated. We can measure up to 8 individual fans for a fan array or fan wall configuration, get individual flow rates back to the transmitter, have analog and network output connections, whatever you need. And we also have fan status alarm here. So you could set this fan wall and fan array up, and you could say, if any one of these fans gets outside a 20% predetermined set point, it alarms the transmitter, and you can take that alarm output to your system as well. So really great product. Again, these don't have to be recalibrated. We see a lot of piezo rings still, which is differential pressure. I'm not going to get into technology differences, but the one thing I will say is if you wanted differential pressure piezo ring to perform the same as this, you got to specify a 0.1% pressure transducer in your spec, and you have to have a transducer on each individual one of these, because that's what we're doing. We're measuring at each individual fan. And again, our sensor accuracy is plus or minus 2%. We also have damper flow meter combinations, all in one easy package to use with a really high quality Tamco damper. We have the AirIQ, the AirIQ2, outside air intakes, unducted returns, for example, for the AirIQ. So we do have that partnership with them. When I was talking about stack effect, this is a potential solution for this, measuring on each floor or each zone level with this type of flow meter damper combination. And then to close, for CO2 DCV, again, we do have a relative humidity. We have a CO2 sensor, but really want to recommend setting those upper and lower airflow limits to save energy and to make sure you're not underventilating the space if you are doing CO2 DCV. But we also have the census occupancy counter. This is what it looks like. Goes over the door, and basically what it is we have 2 thermopiles there, and it's measuring the the thermal signature as you pass through it, and it sees a spike in thermal signature. And these are pretty cost comparable to what you'll see with the traditional self-calibrating CO2 sensor. So I hope you all enjoyed. Now, if you do have any questions, I will stay on the line here for a second and feel free to ask any questions. Or if you have specific questions, you can always send them to sales@engineeredsalescorporation.com.